Welcome to The Explainer. Today, we're jumping into a story of innovation that's been 60 years in the making. We're talking about a fundamental problem in computer science, one that powers so much of our digital world, that was just solved in a way pretty much nobody thought was possible. And it all kicks off with a question you probably ask every day.
Seriously, think about it for a second. When you pull up a map on your phone, you ask it something that seems super simple. What's the fastest way to get from here to there? But behind the scenes, your phone is looking at millions, sometimes even billions of possible paths through a crazy complex network of roads, and it spits out the single best answer in just a few seconds. That little bit of magic? It's powered by something called a shortest path algorithm.
And get this, for the entire history of modern computing, one single, elegant algorithm has been the undisputed king of solving this. It was considered so flawless, so optimal, that the idea of improving it for the most common types of networks was thought to be, well, impossible. But a team of researchers just went and proved everyone wrong.
Okay, so to really grasp why this is such a huge deal, we first need to get crystal clear on the exact problem this old champion was so good at solving. It's what computer scientists call the single source shortest path problem, or SSSP for short. So, single source shortest path, SSSP, isn't just about finding the one route to your one destination. No, it's about calculating the fastest way from your single starting point to every other possible point in the whole network. And this is absolutely crucial, not just for roadmaps, but for things like routing your data across the internet or analyzing how people are connected on social media. It's truly one of the foundational building blocks of our modern connected world.
So how did we tackle this for the last 6 decades? Well, it all comes down to one brilliant and deceptively simple method. It's time to meet the reigning champion, Dijkstra's algorithm.
I want you to picture it. The year is 1959. Computers are still the size of entire rooms. And a Dutch computer scientist named Edgar Dijkstra comes up with an algorithm that is so simple and so incredibly effective that it becomes the gold standard. I mean, for over 60 years, if you took a computer science class, you learned Dijkstra's. It was, for all intents and purposes, considered the perfect solution.
Now, to really understand what makes Dijkstra so special, it helps to see it next to the other classic approach. You can think of Dijkstra's algorithm as the perfectionist. It always asks, of all the places I can get to right now, which one is the absolute positively closest? It picks that one, locks it in, and never ever looks back. On the flip side, you have the Bellman-Ford algorithm, which is more like the brute force explorer. It just kind of checks all the possible paths, again and again for several rounds, hoping it'll eventually land on the shortest ones.
And the method itself is just beautiful in its elegance. So you're at the starting point, right? The algorithm looks at every single road leading away from you, and it picks the absolute shortest one to the very next town. Then, it locks that path in as perfect and repeats the whole process from all the places it now knows about. It just methodically builds out this perfect map of paths, one tiny step at a time, never second-guessing itself.
But here's the twist. The champion's greatest strength, that relentless perfectionism, is also its hidden weakness. A weakness that created something that everyone in the field called the sorting barrier.
Think back to that core step. Choose the single closest neighbor. On a small map, that's no big deal. But on a huge network with millions or billions of points, like, say, the entire internet, that list of possible next steps, what they call the frontier, can get enormous. And at every single step, Dijkstra has to sort through this giant list to find that one single best option. That sorting process, it becomes a massive computational bottleneck, a wall.
And this belief was just, baked into the field. The community basically figured, well, to find the shortest path, you have to sort things by distance, right? And since Dijkstra's is the best at that, it must be the best possible algorithm, period. That sorting barrier wasn't seen as a flaw in the algorithm, it was seen as a fundamental law of the problem itself.
But what if that whole perfectionist approach was the wrong way to think about it? What if you could find the shortest paths without perfectly sorting every single option along the way? A new team of researchers asked that exact question, and, well, their answer changes everything.
The researchers behind this paper had this beautifully simple insight, and they state it right here.
Instead of trying to sort this massive frontier of millions of points, what if you could just intelligently shrink that frontier down to only a handful of the most important ones?
And their method is just a brilliant hybrid. It basically mashes up the strengths of both of our old champions. First, it unleashes the brute force explorer to quickly gobble up all the easy, obvious paths. Then, and this is the new part, instead of sorting everything that's left, it strategically identifies just a few crucial pivot points, and only then does it bring in the perfectionist, running that super precise Dijkstra search, but only from that tiny manageable handful of pivots.
This is the genius of it. It completely sidesteps that sorting barrier because it refuses to play the sorting game for the whole network. It cleverly combines the raw speed of the brute force approach with the laser focus of the perfectionist, but it only uses that precision where it's absolutely necessary. It's the ultimate work smarter, not harder strategy.
So, okay, a new algorithm is faster. Big deal, right? What does this actually mean in the real world? Why does this theoretical breakthrough actually matter to you and me?
Now this right here, this is what the breakthrough looks like to a computer scientist. It's called Big O notation, and it's how they measure an algorithm's speed. Now look, you do not need to understand the math, but you need to see this. For 60 years, the best possible time had a simple log n in it. The fact that these researchers found a way to make that exponent times less than 1 is the cold, hard mathematical proof that they smashed a barrier everyone thought was solid rock.
So what does all that math jargon mean for the rest of us? In plain English, it means a huge speed up for the most common types of networks out there, what we call sparse graphs. And these are networks where the number of connections is pretty small compared to the number of points. Think about it, that's exactly like a road network, right? A city has millions of intersections, but each one only connects to a few other streets. This directly applies to your GPS, to how the internet routes information, and even how we understand connections on social media.
And that brings us to the final, powerful mic drop from the paper's own abstract. For 60 years, Dijkstra's algorithm was considered optimal, untouchable. This new result is the first to definitively prove that it is not. It's a fundamental shift in how we understand one of the most core problems in all of computing. And this just leaves us with a really fascinating question to chew on. If a problem that was considered completely solved for over half a century can be cracked wide open like this, it really makes you wonder, what other fundamental assumptions are we making? What other perfect solutions are just sitting there waiting for the next brilliant idea to come along and break the barrier?